I am in MEGR 3241 at UNCC, and we built a GPS data logger using a Raspberry Pi 4 and a USB GPS sensor. The GPS sensor has a sampling rate of 10 times per second, or 10 Hertz. Looking at the Raspberry Pi, this connection is for the power, and the GPS sensor is plugged into one of the USB ports. I took the cover off my case so you could see the actual Raspberry Pi 4. Moving on to the software side of things, this is what the desktop of my Pi looks like. To convert the Pi into a GPS logger, we had to use the Pi terminal, which is over here, to get code off of GitHub. The file that actually runs and collects the data of the USB GPS receiver is called gpslog2.py and was written using Python. I'm going to run the file and show the execution terminal so you can see what the data collection process looks like. So this is what it looks like when it's collecting data. I'm going to go ahead and stop it. And it generates a CSV file, like this one shown here. Here we go. As you can see, there's not much change in the numbers, and that's because the GPS sensor is not moving. This is the raw data that was generated during my 2 runs. I chose to use Excel to analyze the data. This is the raw data for both polls and the graphs that I generated here, which I will go into more detail analyzing later on in the video. To collect data, I did 2 0 to 60 mph pulls in my 2008 Mazda 6 with a 2.3 liter 4-cylinder. One of those pulls was uphill and the other one was downhill. Because I was on public streets, I wasn't that aggressive, but during both tests, I held about 75% throttle for the duration of the pull. This first graph is the raw GPS speed data that was collected from the 2 runs. The blue line is the downhill run, which was the first clip that was shown, and the orange line is the uphill run, which was the second clip that was shown. To better compare the 2 runs, I removed all the data from when the car was not moving. Now we can see that the slope of the downhill run was greater than that of the uphill run, which means there was greater acceleration. The time it took to reach 60 mph during the downhill run was also about 2 seconds less. The hump in the uphill run, around the 3-second mark, was due to the fact that I had to make a left-hand turn across the road before I could really open up the throttle. This next graph shows the change in altitude during both the uphill and downhill runs. This graph shows the heading or direction of both runs, and you can see where I turned right into the road for the downhill run and left for the uphill run before I straightened out for the 0 to 60. This is a table that summarizes the data I collected. The average acceleration of the downhill run was about 7.2 feet per second squared, while the average acceleration of the uphill run was 6 feet per second squared. The total 0 to 60 time of the downhill run was 13.4 seconds, while the 0 to 60 time of the uphill run was 15.8 seconds. The altitude change was about 35 feet for the downhill run and 20 feet for the uphill run.